All right, Gen Chem, today we are going to start a new chapter, chapter 15, reaction rates. Sometimes it's called reaction kinetics or kinetics of reaction. So when we talk about reaction rates, we're going to talk about them in concert with kinetics, which is the movement of particles. So we're going to explain how reaction rates can be changed with different particle motion. So let's talk about really quickly, first thing, what we mean by a reaction rate. Now, a rate is how quickly something happens, okay? So a rate is a change in something over a change in time. So we're talking about how fast a reaction will happen. So we're talking about how fast a chemical reaction will happen. And we usually measure this by the change, and I'm going to use the delta symbol because in the Greek alphabet that delta means change in usually the mass or the concentration of a product. So we'll measure a product of that reaction and we'll see how quickly it changes mass, like how much we can weigh of that product or how concentrated that product would be. And we usually measure that in terms of time. Sometimes the time will be quick, like per seconds or minutes, sometimes even hours. And you saw when we did half-life, sometimes the half-life was days or years. So sometimes these reactions take place over really long time. So that something is usually a change of one of our products. We can also kind of change it by measuring how quickly one of our reactants is used up, how much mass we lose of our reactants, or how the concentration of our reactants goes down. But we usually measure it in terms of a product. Okay? So there are several things that affect the reaction rate just by changing how the particles are. The first one is the nature of the reactants. So if I have a reactant, say that's a small little molecule, there's only a few places on that molecule that I can hit that molecule. Not very many options of how I hit that molecule. So that reaction is going to go a lot faster than if I have a really large molecule. Say I have a really large like protein, and right here is the place that's reactive. But look at all these places I can hit this molecule. I can hit this molecule all over, but I have to hit it. I should put this one in red. I have to hit it right here for it to work. But all these other places I can hit, that molecule is not going to work. It's not the active site of that molecule. So the smaller the molecule, the more chance I have of hitting the right place. So let's write that down. The smaller the molecule, and we can say particle or molecule, the better chance I have of hitting the right place for a reaction. So smaller molecules end up usually having much higher reaction rates because there aren't that many places for that molecule to be in contact with the other molecule that it needs to react with. Concentration. Let's think about this. If I have a bin that just has a few molecules in it, or if I have a bin that has a bunch of molecules in it, which bin has a better chance of hitting another molecule? This one does, right? All reactions have to happen because we are hitting molecules together. And the more chance we have of hitting molecules together, the more chance we have of actually having a reaction happen. So higher concentration gives us a higher probability or chance that a molecule will hit another molecule or collide with another molecule. Okay, so the more I can increase that chance of actually hitting another molecule, the more chance I have of that molecule actually having a reaction. So a higher concentration gives us more of a chance than something with a low concentration. There isn't much of a chance with so few molecules that those molecules are actually going to come in contact with each other. Okay, I will upload a video showing you how concentration affects the reaction rate. The next thing that helps us actually have a good reaction is having a catalyst. Now, if I look at these energy diagrams, I have energy on my y-axis, and on my x-axis, this is actually time. It's the progress of a reaction. In a normal reaction, I start out here with my reactants, and I have to put in this much energy. This is what we call the activated complex. It's the activated complex. And this energy that I have to put in here is the energy I need to break reactant bonds and start forming product bonds. So I have to break reactant bonds, and then I have to form bonds of the product. And that takes energy to break bonds and to form new bonds. Okay? And there are only a couple molecules that actually have enough kinetic energy to put in all that energy. So if I can put in a catalyst, now catalysts give us a different or an alternate way of reacting, an alternate pathway. Catalysts are not used. They are not used, okay? They provide an alternate pathway, okay? So are not used or consumed, and they provide an alternate reaction pathway at lower energy. Okay, so if we look at our catalyst here, our catalyst line with the catalyst, we don't have to put in nearly as much energy. So we will actually have more molecules that have that kinetic energy that can get to here. So because we have more molecules that can actually have that amount of energy, we will have more molecules reacting. So we actually get more products, and it will actually speed up the reaction because of that. Same thing here. Notice the energy required with the catalyst compared to the activation energy without a catalyst here. That catalyst provides us another pathway or an alternate pathway with a lower energy profile, So more molecules actually have the energy that it takes to complete that reaction. Okay? And remember, catalysts are not used up in the reaction. They're they help along. They're kind of like a helper. And then when the next molecule comes along, they can take a next molecule. They are not used up in the reaction. Okay. Surface area. Surface area is a huge one. Now think about this. If I had a fire and I put a wood fire, think about a campfire. If I have a normal campfire, I usually put on big chunks of wood on that fire, logs, big limbs, big branches. Where on that wood does the fire actually burn? It burns just on the surface. So it takes a long while for that fire to actually get into the center of the wood or the log because you have to burn off all the surface. So reactions can only happen where the reactants, the air in this case, and the wood can come into contact with each other. So reactions only happen on the surface. And they only happen on the surface because the reactants have to be able to become in contact with each other. So a big wood fire and a campfire, that log only burns on the surface. What if I took that log and put it through a chipper or made sawdust out of that log and then put that sawdust or wood chips on the fire? What would happen to the rate of the fire? Think about it for a second. If you've ever seen a handful of sawdust thrown into a fire, it creates a fireball. It's actually a really dangerous situation because the surface area of that wood is now everywhere because the particles of the wood are so small that there's surface everywhere. And so it all burns all fast. Okay, so sawdust. We have really increased the surface area. So the fire burns fast. And it burns it all instantaneously. Okay? So the more surface area that I have, the more ability I have for the reactants to get in contact with each other and actually react. So I can speed up a reaction by increasing the surface area. If you've ever taken an Alka-Seltzer tablet and put it in water and then taken another Alka-Seltzer tablet and crushed it up into little fine crumbs, the crumbs will be used up just like that, where the tablet takes a while to dissolve. So if I can increase that surface area, I'm going to increase that reaction rate. Okay, temperature. Temperature will always, if I increase that temperature, it will always cause an increase in the reaction rate. And this is why I've been saying over and over that for something to react, I've got to get it to collide, right? The reactants have to collide with each other. So if I increase the temperature, what happens with the speed of the molecules? Doesn't an increased temperature, faster molecules move faster, right? Hotter molecules move faster. So the molecules move faster. And if they move faster, aren't they going to collide more often because they're just traveling faster? Yeah. So the molecules collide more often. So because I have more collisions, more of those collisions are actually able to produce a reaction. So more collisions equal more molecules reacting. So the more I can speed things up, the more collisions I'm going to have because they're moving around even more and more energetic, and the more molecules I will have reacting. Okay, so let's talk about this, collision theory. Now, collision theory states that all molecules have to collide in order to react, okay? So molecules must collide in order to react. And we've talked about that a bit so far, okay? But they have to do more than just collide. Every collision does not produce a reaction, just like we set up here. If I have this big, huge molecule up here, I can have all these collisions, but only the red one's going to actually create a reaction because I have to hit on the right part of the molecule. Okay, so that's one of the things that has to happen. In order for a reaction to occur, there must be a meaningful collision between particles. A meaningful collision must involve two things. The first thing is we have to hit on the right part of the molecule, or the molecule has to be oriented in the right way. So the collision must be in the proper or right, correct orientation. That's just a fancy way of saying the right part of the molecule has to hit the right part of the other molecule. So the correct or the right part of the molecules must collide. Okay, so the correct or the right part of the molecules must collide with each other. Otherwise, it's not going to react. Okay, the other thing that has to happen is the molecules have to collide with enough energy to actually make that activated complex. And we talked about that a little bit in this energy diagram. I said that we had to have enough energy to break the reactant bonds and start forming new bonds. So not just colliding with the right spot, I have to collide with enough energy to actually start breaking the reactant bonds and start making the product bonds. So I have to have enough energy in the collision. So our next thing is the collision must have enough energy. Okay, so think about it this way. If you've ever been to a demolition derby, there's one goal in a demolition derby. Your car needs to be the last car that's drivable. So you need to hit all the other cars in a way that makes them so that they are undrivable. So if I'm driving my car and I hit the trunk of all the other cars, does that really help me make the other cars undrivable? No, because I'm not hitting the right part of the car. I need to hit the other cars in a way that damages their engines so that it doesn't allow it to drive, okay? Number two, so that's hitting in the proper spot. Number two, if I'm in a collision in a demolition derby and I'm driving my car 5 miles an hour, so I'm not hitting anything very hard, am I going to damage the cars that I hit? No. I need to collide going fast enough to have enough energy in the collision to actually damage the other cars. So when we collide to have a reaction, those two things need to happen. I have to hit with enough energy and I have to hit on the the proper part of that molecule to get it to react with the proper orientation. So let's think about this. We have carbon, nitrogen, and oxygen right here. And I'm trying to get the carbon monoxide, this black and red molecule, to hit nitrogen dioxide and actually take one of the oxygens off of the nitrogen dioxide and put it on the carbon monoxide to make carbon dioxide. Okay, so if I have the two oxygens hitting, that's not the proper orientation. I need the oxygen from the nitrogen dioxide to be hitting the carbon. I need it to hit over here. So that's not the right orientation. So same here. I don't want the oxygen hitting the nitrogen. I want this oxygen hitting the carbon over here. So it's going to rebound. It's not going to react. I could have the correct orientation where the oxygen is hitting the carbon. That will work. Notice now I do have carbon dioxide and nitrogen monoxide, just like I wanted. Or I could even have the correct orientation, but this is a weak collision. It's not very strong. It's insufficient energy. It will still rebound. So I have to have the proper orientation and I have to have the right amount of energy. Okay? So next time we will start getting into reading these diagrams, these energy diagrams, and start getting some of the information off of that and telling whether a reaction is exothermic or endothermic, and telling us how much energy there is in the activated complex and all of that kind of stuff. So we'll do that next time. Have a great time. We'll see you next time. Bye.